I have been dying to understand quantum computing. And listen, I majored in computer science. I went to graduate school for computer science. I was a computer scientist for many years. I've taken apart and put together conventional computers. But for a really long time, I keep reading these articles about quantum computing and it's like magic. It can do anything. And I've been really trying hard to research it and really understand it, but it doesn't go along with the conventional ways of understanding computers. It's a completely different paradigm of doing computing. So I asked on two friends of mine to come on the podcast. Nicolas Newton, he's the COO and co-founder of BTQ Technologies. It's a quantum computing company. It's a publicly traded company, BTQ Technologies. And what they do is they solve the issues of quantum security. So once there's quantum computing, according to all these articles, things like Bitcoin will be hacked and we'll be in trouble. But this company that Nick started or helped start is going to help solve this problem of quantum security. So I invited Nick Newton on. I invited Gavin Brennan on, who is a top quantum physicist who also works with this company. And I really wanted them to explain from the ground up, what is quantum computing? How quickly will this change the world? Like right now, there's no use cases. There's no really useful use cases for quantum computing. Even Google has said so. Even NVIDIA has said so. It's years away. But when will it be an issue? Turns out, actually, it's an issue right now for reasons I didn't quite expect. You'll hear about that in the podcast. Gavin and Nick explained to me exactly what quantum computing is, how it works. I try to simplify it even further, so I hope people can understand, although feel free to tweet me any additional questions or tweet to them any additional questions. And I then wanted to understand, how are we going to deal with all the security issues, even on a national security level, like what is going to happen? So these guys were really patient with all my dumb questions. Pay attention. I think quantum computing is a game changer in computing, and it's very important to understand what the issues are. So here's Nick Newton from BTQ Technologies and Gavin Brennan.
This isn't your average business podcast, and he's not your average host. This is the James Altucher Show.
Nick and Gavin, before we get into the complicated issues of quantum security, I am desperate to understand. So I have a computer science background, went to graduate school in computer science, been doing this a long time, but I don't even know where to begin trying to understand what quantum computing actually is. And I know it's very complicated. I'm not going to understand everything, but maybe we could start there, just like in layman's terms, if possible. And I'll try to also every now and then stop you and ask questions to understand further. But what is quantum computing? How does it work? How do I do a quantum computation?
Yeah. So I'll take that one. So I like to think of it as kind of a magic box where you stick information in, just like any other normal computing. It's really no different. The idea of computation as a process is the same when you're using a laptop as using an abacus. You stick in some initial state and do some processing, and then you get out some information. And the information you put in, initially you could just write it down on paper or type it in. We call that classical information because it's just something that lives in our normal classical world. And then when it goes into the quantum computer, there's a process that uses the laws of quantum mechanics, which we've known for over 100 years now. And it will be able to process information in what's called superposition. So it's just, you're not just doing things on, like an all zero register or, a particular string of zeros and ones. It's all possible strings of zeros and ones. And if the algorithm is written to work well for your problem, it will reinforce the good solutions to the problem and destructively interfere, which kind of subtracts out or cancels out the wrong solutions. And it will do this in a way that's fast.
I'm gonna stop you there because I'm gonna try to break down what you said.
Yeah.
So, and by the way, can I just ask, what was your background in quantum mechanics and physics?
Yeah. So I'm a professor of theoretical physics working on basically quantum computing at Macquarie University in Sydney, Australia. And my work originally started on an architecture for a quantum computer based on atoms. So that was what my first work was.
Are atoms too big for a quantum computer to work on?
No, the atoms are a great qubit to work with because they're the same anywhere in the universe. You don't have to manufacture them.
So a qubit doesn't have to be made out of like quarks. It could be atom size.
Oh yeah, yeah, absolutely.
And Nick, can I ask? So you're obviously the CEO of the company BTQ Technologies, or the co-founder with your brother Olivier. What's your background in, like, you were just fascinated by the area. How did you kind of get the knowledge to understand what was going on?
Sure. Yeah, I come from software and computer science, but just growing up in Vancouver, Canada, where quantum was really first commercialized. So pioneering companies like D-Wave Systems on the hardware side, and One Qubit on the quantum algorithms and software side. So just had exposure through that, and always had an interest in starting a company in the space. And had a chance to meet Gavin many years ago now through our mutual interest in both blockchain technology and quantum, or the intersection of cryptography and quantum computing.
So Gavin, in terms of what you said, that the algorithm will get you, I forgot the exact words you used, but will get you closer to a solution. Like in a classical computer, if I want to figure out what the factors of 100 are, meaning like what numbers are divisible into 100, I'll go one number at a time. Like, okay, 2 is, 3 isn't, 4 is, 5 is, 6 isn't, and so on. And in a classical computer, the input might be, okay, is 7 a possible factor of 100? And the computer will either come back, using its circuitry and built-in functions. It'll either come back with a 1, yes, it is a factor, or a 0, no, it isn't a factor. And then it'll go on to the number 8, the number 9, and so on. And how is that different from what you just said, which I think is very different, which is that somehow the algorithm gets closer to resolving on an answer?
Yeah, that's right. So it works on all the possible attempts in superposition. So that just means that, like when we learn vectors in school, you can write it down on a piece of paper where you have a bunch of components of a vector. And here, each component would correspond to a different bit string. Those bit strings could represent potential factors of the number, like 100. And it will act on all those at the same time. That, together with being able to reinforce the correct solutions and cancel out the bad solutions, will be sure that you get the right answer with high probability at the end.
So it's really interesting because I'm actually, for the first time, even though we've only been discussing for a few minutes, after many months of reading about this, I'm starting to understand. So let's say I throw in the number, 8 into the computer as input. The bits are 100, which is the binary for 8. If I'm not more, maybe that's 4. I don't know. I'm already messing up. 1000, 1 and 3 zeros, and in a quantum computer, because every bit is arranged between 1 and 0 until it's measured, right? So when you say superposition, that means we don't know yet whether the qubit, the quantum bit, we don't know whether it's a 1 or 0. It's a range of probabilities between 1 and 0. So now, Because if I'm dealing with 4 bits, to get, like, for instance, up to the number 8. If I'm dealing with 4 bits, I can look at all the numbers from 0 to 8 simultaneously because they're all the bits. But while it's still in superposition, which we can explain in a second, while it's still in superposition, at one time, I'm looking at all the possibilities between 0 and 8, not just the number 8.
Exactly. Yeah.
And so depending on how the algorithm is written, it'll collapse on the right set of numbers that all are factors of 100.
Yeah, that's right. And sometimes you'll hear people say that quantum computing is about parallelism and, living in the multiverse. And the problem with that is that, yeah, sure, you can do everything in superposition, but if you don't also have this process of reinforcing the correct solutions, then you only have like an exponentially small probability of measuring the right answer. So you need both. You need the parallelism working all in superposition, and this interference effect where you get, plus signs and minus signs, which you don't usually get in normal computing.
What do you mean plus signs and minus signs?
So, you might get something where as you're doing the computation, you'll get, it'll act on these different paths, the different strings all at the same time. But maybe if, the state 101 is the right solution, you'll have two components that add up to 101 components, and the 111 components will cancel out. And so in the end, the only string that will have appreciable probability is the correct string.
Or multiple strings, or no?
It could be multiple strings. Maybe there's multiple solutions.
Right.
Or, maybe there's a small probability that your computer didn't get exactly the right answer, but if you repeat the whole process a constant number of times, you will get the right answer.
So okay, this brings up other questions, which is, so maybe try to explain superposition, and then I'll interrupt you if I have questions or want to see if my explanation in a different way works.
Yeah. So, you could just start at the lowest level, a single bit. If a bit you would write in paper would just be 0 or 1. And a superposition of a quantum bit would be, we would call it alpha 0 plus beta 1, where alpha and beta could be complex numbers between 0 and 1.
Now, is this because, so in superposition, in quantum mechanics, there's this idea that before a particle, like an atom or a quark or whatever, before a particle is measured, it actually doesn't have a solid location or spin direction. I'm trying to vaguely make sense of what the little I know. So, which in the classical physics world, everything has this fixed location at all times. But in the quantum world, something doesn't really exist in a particular state until it's observed, until something happens to it. Otherwise, it's just in a probability of states for every atom in the universe.
Yeah, that's exactly right.
And so, just as I'm going to ask super dumb questions. Obviously, we're all made up of a bunch of atoms. Is every atom that makes us up just basically in a undetermined state until we look in the mirror, or what's the story with just atoms in general?
So human beings, what we say is we're wet and warm. So wet means that things are interacting really strongly with each other, and we're warm because, our everyday experience of temperature is really warm compared to the coldest temperatures you get when these quantum effects really start to play a big role, which is usually temperatures around absolute zero, so minus 273. And so humans, as far as we know, don't really experience quantum effects. There is some research to look into that, but we don't see those effects so strongly. But when you start to get very cold and you isolate systems, and that's why if you look at these photos of the Google quantum computer, you see this massive kind of chandelier looking thing. That's not even the chip. That's all a series of refrigeration units to get the superconducting qubits they use cold enough so that the quantum effects really start to come into play. And when you get that, then exactly as you say, you have these states that cannot be described as just up or down, or the spins pointing in a certain direction. They're really in a superposition, and you can force them by measuring them to be in a particular state, which But before then, you have to really describe them as superposition states.
Take a quick break. If you like this episode, I'd really, really appreciate it. It means so much to me. Please share it with your friends and subscribe to the podcast. Email me at altucher@gmail.com and tell me why you subscribed. Thanks. Have you guys seen the TV show Dark Matter on Netflix?
Oh, no, I haven't seen that.
So it is sort of a multiverse kind of science fiction show, but the idea is this guy puts himself in this box and then knocks himself out. So in a weird way, nothing is observing him, and then at that point, when he wakes up, he could be anywhere in some other parallel universe, and it's kind of supposed to be like quantum mechanics. I know it's not exactly, because you can't do that, but that's how they get that idea in this science fiction show.
Oh, I have actually seen that. Yes, I remember that now. Actually, I kind of enjoyed that show.
Yeah. And so it reminds me of what you're saying. So basically, you take this particle, and by putting it at absolute zero, nothing is interacting with it. So the universe and this particle doesn't know where this particle is. There's no way to actually measure this. It doesn't have a particular location or spin until you make it higher than, until you measure it, until you remove the absolute zero conditions and it starts interacting with things, and now it can be measured. But until then, and this is the key thing, until then, it's not like that we just don't know the location. It has no location. It's all possible locations.
Yeah. Yeah, that's right.
And we don't really know why this condition of the universe exists, right? This is the whole big issue in physics. We don't know how to unify classical physics and quantum physics. Like, do we know why quantum mechanics even exists?
Well, what's really been interesting is quantum mechanics is in some ways very simple. It's what we call linear theory. If you have a superposition of states, the physics acts as just a sum on each component of that. Gravity is not. Gravity is highly nonlinear, which makes it a total mess to do calculations. And I'm actually glad I don't do gravity as a day job, because it gets really ugly.
Who does do gravity as a day job? I feel like construction workers do gravity as a day job.
Yeah, maybe. And we don't know why they don't work together. It's still one of the biggest outstanding mysteries in physics.
So again, because a qubit, which is the quantum computer version of a bit, represents it doesn't just represent a 1 or a 0. It represents a particle that's in the superposition. It might be when it collapses, it might be a 1, it might be a 0, but at that moment, a single qubit is this whole range of numbers, I guess, between 1 and 0. And so if you have multiple qubits, you can basically look at all inputs simultaneously if you're trying to figure out a solution, as opposed to one input at a time. So again, in the issue of like finding the divisors of a very big number, the factors of a very big number, with a classical computer, you have to look one at a time. A quantum computer looks at all the numbers at the same time, because it's simultaneously, all the qubits are simultaneously all the probabilities, like infinite number of probabilities. Is that roughly what's happening?
That's right. And you get some strange effects. For example, normally when you do a little bit of introductory code, you might write a while loop, while loops people know. You do some process and you check to see if a condition is met, and then you jump out of the loop. It's very hard to do while loops in quantum mechanics. You have to rethink things because you can't check a condition the same way you would on a normal computer, because checking a condition would be like measuring your computer, which would destroy that superposition you keep to get the advantage.
But it
So
isn't even doing any kind of interference at all. Like you say, you have to interfere a little bit to nudge the algorithm towards a solution. Wouldn't that collapse the superposition immediately?
Yeah, so there are some tricks you can play. We call it it's the effect of kind of a weak measurement, where it doesn't force all of the computer to a particular state. It just modifies it so that you still keep enough of the superposition there to continue to do further computations. So you're getting partial information and using that as updates.
And so, do you have to have more qubits available to you than you're actually operating on in order to?
Yeah, absolutely. Yeah, that's a
I
big
see.
part of
So,
it.
like Google's Willow had apparently 105 qubits,
Yeah.
and but the problem that they solved, which they said it would take a septillion years for a classical computer to solve, and they did it in seconds. Did that use all 105 qubits, or was the main input only like 10 of the 105 qubits, and the rest was used to be sort of throwaway qubits that could collapse and then be used to maybe rewrite the algorithm on the fly?
Yeah. So in that case, they did use all the qubits, but it happened to be one of the things about that problem is that it's a completely useless problem. So
Right.
it's but you're absolutely right. So when they're going to scale these things up, there's going to be a lot more qubits that will be there to handle what we call error correction. And quantum computers are just very fragile. Your cell phone uses error correction when communicating, but normal computers, for just internal processes, error correction we don't think about much, but it's going to be one of the most dominant things that quantum computers do, just trying to keep its own internal world quantum.
Well,
And yeah.
because let me understand, like, and this is the scalability issue with quantum computers. So Google's Willow has 105 qubits. Just so people understand, like a lot of people every day, and this is related to the whole reasons for your company. A lot of people ask me every single day, "Oh my gosh, is Bitcoin dead because it's going to be hacked by quantum computing?" Apparently, you need 15 million qubits to even approach, breaking Bitcoin's cryptography. Google, instead of having 15 million qubits, they only have 100 qubits, and every qubit you add, from what I understand, increases the difficulty that you're going to have correct answers because qubits could interfere with each other. So every qubit you add is another potential source of interference that just ruins the whole thing.
Yeah. And if you just like kind of just start to think about it, it sounds hopeless. You're
It
trying to
does.
get a bigger thing to act in a way that nature doesn't want it to act. Nature tends to want to make things look classical. Um, and but it turns out that if you use some clever encoding, so each qubit is actually represented as a logical qubit using many qubits. Say, let's say you use 9 qubits to represent a logical qubit. That's called a redundancy. And we do this also with classical codes. So instead of just having a single zero be a zero, you say you represent a zero as 3 zeros, so 3 bits. And then 3 ones would be a 1. And if one of them flips, you can still do a majority voting and get the correct answer. Well, you can do the same thing in quantum mechanics. You just have to kind of do your majority voting in different rotated bases. But you can do it. And if you make the codes big enough and sophisticated enough, which fortunately we have years of research now shows how to do this, then you can make things so that you can get the error at the logical qubit level low enough that you can get your computation that you want to have done.
So, okay, so that's with redundancy. But let's say now I want to make a quantum computer with 1,000 qubits. Okay,
Hmm.
and none of the qubits are. It's like a party where everyone's wearing a mask. None of the qubits are allowed to like look at each other, or else the whole thing collapses and they're not in superposition anymore. And uh, with conventional computing, since the 1940s, everybody knows how to scale conventional computing. Basically, conventional computing is a mathematical model related to, let's say, if something's to be on a Turing machine, and then you just have to squeeze as many transistors as possible into your chips. And the more you squeeze in, the more every year you're going to squeeze more and more. You're going to make the transistors smaller and smaller, and the computers are going to grow. But do people know how to scale quantum computers? Everyone knew how to scale conventional computers ever since there were vacuum tubes in conventional computers. Do people even have an idea how to scale a quantum computer?
We do. So there are some caveats to that. So we basically know how to design these error correction codes, how to do the checks for errors and correct them, and how to do the processing. But there are a lot of engineering challenges still. So, for example, at some point, like you say, you're getting so many qubits you have in there. When you're starting to reach the level of hundreds of thousands, you can't fit all those in a single chip. Basically, you can't get all the cooling down to handle for like superconducting. You probably can't get more than 5,000 in a single chip, and then you have to connect chips. Well, how are you going to connect those? Well, there are ideas. You can use what we call transducers and interconnects, which carry quantum information. But actually, building these things is difficult. And so most of the big quantum computing companies now are focusing on that as one of their main problems.
Which is how you make like for instance, I see these pictures of Google's quantum computer. It
Yeah.
looks big, and like you say, it's because of all the cooling, and that's for just 105 qubits. Each qubit's like the size of an atom. So how are you going to make something with 1 million qubits? And I'm sure people asked the same question in the 1950s, but I feel like there was more of an understanding that, okay, eventually it will happen. Whereas here, I don't see how it could possibly happen.
Yeah, I mean, well, you can go to the IBM website and you'll see they have this kind of structure where they have objects that look, each module carrying chip is represented by a hexagon, and they connect these hexagons together. Um, for atomic systems, they'll have arrays of a few thousand trapped atoms, and then these arrays will be connected by optical interconnects. Um, yeah, I mean, there are ideas, but you know, it remains to be seen. So that's really where we're at.
When you say optical interconnects, is
Mm.
there any particle that is so, let's say, massless that it doesn't really interfere with a qubit? So, for instance, does light interfere with a qubit so that it collapses the qubit to a 1 or a 0?
Yeah, so light is a very good qubit in a way. When we look at starlight, that's coherent over most of its travel. It could be, many thousands of light years, where a single photon, was in a certain direction, and that's like a qubit. You could call this a 0, this a 1, and in between a superposition, and that will travel for, thousands of light years. So it's, in a sense, a very good qubit. It's hard to make light interact with other light, but there are companies that are building light-based quantum computers. PsiQuantum, Xanadu, Quandela, and that's their goal, to exactly use that kind of qubit. And it is absolutely one of the promising architectures.
Nick, when you were initially conceiving of the idea of BTQ Technologies, and again, you deal with BTQ deals with quantum security. Did you feel this was a problem that needs to be solved now if we don't even know if quantum computing will get to the point that it's actually useful within a certain number of years?
Yeah, for sure. And we started working on the company about a decade ago. And this was about the same time that the US government and the National Security Agency and NIST, the standards agency, started this process to upgrade security standards on the internet. So after a decade of research and input from the community and large companies, this past August, there were a series of algorithms that were standardized, and those are thought to be quantum safe. And the reason why people are adopting these algorithms today is because, one, there's this risk that adversaries can just store encrypted data and decrypt it when they have a working quantum computer.
So let me ask you about that. So someone could basically hack into a bank, let's hypothetically, get all of the usernames and passwords, not be able to, not be able to decrypt any of the passwords right now because classical computing can't do it. But let's say 10 years from now, quantum computing can finally do it. Some of those passwords will still apply. They can now figure out 100% of the passwords. Some percentage of those will still be being used by those users. And so people who take snapshots of the world now, even if they can't understand what that snapshot says, will be able to understand it once quantum computing hits, and they'll be able to then, go into the accounts of anybody who didn't change their passwords on a regular basis.
Yeah, sure. So I think there could be a lot of encrypted data that's targeted, especially in industries where it's like very sensitive, like healthcare or financial or defense related data, warehouses and so forth. And also just the nature of transitions in cryptography. So like historically, we've done this a few times where we've upgraded like standards, and that process typically takes a decade, just because it's a lot of work. So that's already within potentially the time horizon that you're going to have a lot of innovation in quantum computing. You also have other problems like hardware, for instance, right? So if you're manufacturing a hardware device today, that's going to be out in the field for a long time. And that needs to remain secure against quantum computers. So, these standards implemented by the U.S. government, they're now mandated. So the Biden administration had an executive order, and you're already seeing a lot of internet traffic already, like it's already post-quantum. So Cloudflare, which is one of the largest CDNs, I think they are already published that almost 20% of internet traffic is using some sort of post-quantum cryptography. So you're going to see this get rapidly deployed.
So can a classical computer have an algorithm or a program that can still be quantum safe when quantum computing is here?
Yeah, so that's what the community over the past 10 years is essentially looked at, is how do we develop classical algorithms that can withstand a quantum attack where there's no known quantum attack vectors, essentially.
So let me try to understand that. So from what I understand of cryptography, a lot of it involves, let's say, the factoring of very, very extremely large composite numbers, like a 1 followed by 100 digits. That size number would be impossible basically for a classical computer to factor into its prime number factors, but a quantum computer could do it fairly quickly, again with 15 million qubits. But how do you make something that's, if a quantum computer could basically look at infinite possibilities or almost infinite possibilities, how can you make a classical computer that fights that or that protects against that?
Yeah, so the community, we've been like, it's we've been looking at different types of underlying math problems that can secure cryptography. So we're going to have to move away from the RSA-based crypto that we've been using for the past 40 years on the internet. So that this is a huge change, and I think we're still not sure what algorithms will ultimately be secure. I think there was recently there was actually, so one of the algorithms in this US government process that was studied for years and years was ultimately just broken because one really clever researcher in Europe developed a scheme and published a paper and was able to compromise that algorithm. So I think there's a lot of research to take place. And I think, Gavin, maybe you can speak to some of the quantum algorithms as well that are emerging in terms of attacking post-quantum crypto, because there's been some research in that side of things, if you want to touch on that.
Yeah, so one thing is quantum computers can't solve all problems faster. And in fact, like even some really basic problems, you might think you could get a speed up and it really just can't.
Like what?
Like, for example, the majority problem, like determining whether a string has a majority of zeros or ones. You know, that if you're close to being half zeros and half ones, you have to wait until the last bit to figure out, right? Classically. Quantum mechanically, it's the same thing. You can get a speed of a factor of 2, but that's it. So it's not any kind of major improvement.
That's fascinating, actually, because that makes sense, right? So as opposed to factoring a large digit into its divisors, where you could look at all numbers simultaneously and sort of resolve it that way, there's no way to look at, there's only one state here. When you have just a large string of zeros and ones, there's really only one state. So there's no way to look at a bunch of different states simultaneously. It doesn't make any sense.
And there are other problems that we know that are very hard and very unlikely. We don't have proof, but it's very unlikely quantum computers are going to give us an exponential speed up on.
So it's sort of like when the solution is potentially a list of solutions, like like you're listing the numbers that can factor into a larger number, or you're listing the best, the fastest road trips between New York and LA. That's a list. That's what quantum computers are great at, building these lists out of an infinite number of variations. But when you have, one object which you're trying to understand the properties of, like this object, does it have more zeros or ones? A quantum computer has a hard time with that.
Yeah, and it can get subtle too. Like it gets into ideas from complexity theory, but one of the main classes of problems is finding the lowest energy configuration. So maybe you have a bunch of spins, and you want to find the lowest energy configuration where they can interact with each other in little neighborhoods with their closest neighbors. And this is like a workhorse problem that's used for solving optimization problems. And some of those problems are thought to be exponentially hard to solve for both classical and quantum computers. So yeah, it's quantum is only good on like a few types of problems. Problems where you have big data. Not very good for quantum computers, because it takes a lot of effort to put a lot of data into a quantum computer, and you don't want something that has a lot of input or output of data. Like probably weather forecasting would not be a good application for quantum computers. But if it's something where, like, as you were saying, where you have like something where you can encode the problem, where you can work on superposition effectively, and you only have a few likely outputs, then it's a very good speed up.
So to make something classically quantum safe, first you have to come up with quantum algorithms to make quantum encryption that works. So you have to kind of find ways to encrypt things other than the classical public key cryptography or things like that, which quantum computers can break. You have to kind of have a whole new model of encryption.
Yeah.
And what have they come up with?
Yeah, so there's a variety of them. Like one of them is lattice-based cryptography, where you try to find the shortest vector to particular points in some high-dimensional lattice. We don't have a proof, but it's thought that quantum computers won't be able to solve that problem efficiently. There's others based on hashing, which is just a kind of a basic function you can apply to inputs that scrambles them up. It's thought that quantum computers don't have a way to solve those problems. Again, a lot of these things we don't have proofs for, but there's a lot of smart people that have tried and not found ways to get a speed up with quantum computers on those problems.
But like with these optimization problems, isn't that something that a quantum computer can do very fast, because you just try all possible paths to optimize at the same time and boom, you have a solution?
Yeah, so it's something that's caused a lot of debate in the community. And exactly, that's the kind of the intuition that we should be able to sample the space, and you often hear the words tunneling, where you could sort of use the quantum mechanical effect of being able to explore spaces that you wouldn't be able to do classically, tunneling over energy barriers to find like the lower energy dips in a landscape. But there are a lot of caveats there. So it turns out that for some of these problems, you can't actually get any significant speed up. But it's something that's still being researched. There are certain particular subproblems you can get a speed up with optimization, but it's not sure. It's not clear exactly how much.
So what has BTQ, your company, figured out that you feel should be applied to devices now for a future world where we're going to need, quantum cryptography to keep things secure, to keep data secure?
Sure, yeah. So we've been developing a lot of product lines around so hardware, so making sure hardware remains secure, but also looking at blockchain as well. So you mentioned Bitcoin, all of that is vulnerable to quantum attacks. So people need to build new signature schemes. And the issue with implementing these new US government standards is that they're very large in size. So they're not compatible with existing blockchains. So you need to build compression technology. So BTQ, we've built the leading compression technology to implement those standards within a blockchain environment. And then what we've been working on with Gavin is how do we not just kind of protect against quantum, but how do we harness quantum for things like quantum energy advantage, and how do we implement these NISQ era devices or near-term intermediate scale quantum devices to do something useful. And so one of the problems and one of the solutions that we've built is something called QPOW, or quantum proof of work, where we've demonstrated using a commercially available quantum device today that you can use these kind of quantum miners to perform validation in a network, and the benefit being it's significantly, like in terms of energy cost savings. So there are interesting applications for these near-term devices that we're seeing.
So devices that might even exist in the near term, like Google's Willow.
Well, that already exists. So like some of these companies, I think Gavin mentioned earlier, like Xanadu, they're developing these boson sampling devices. Now they're still expensive, but they'll be much more cost effective than these large scale universal quantum computers. So these are all in the near term regime that we're currently in. But no one's really, I think, looked at the applications for them within cryptography like BTQ has. And I think one of the reasons for that is when you speak with these companies, they're very focused on this long-term vision of breaking, like using Shor's algorithm and running that and running millions of qubits. We've looked at the near term, and I think Gavin's also been looking at some other ideas together with our team on that.
So are you trying to anticipate what future quantum cryptography would look like, and then building secure way, building that classically into, let's say, the current Bitcoin?
Yeah, absolutely. So we can take these standards that have been developed by the U.S. government, and we've also been involved in the standards process. And then, we can optimize that for a specific blockchain use case, because the standards body hasn't been focused on blockchain. And I think it's just until very recently that blockchain developed an interest in safeguarding against quantum attacks. This is technology where we can build replacements, but it takes a lot of work. You'll need potentially a lot of hardware acceleration as well. And then we can also leverage quantum technology in interesting ways, like within quantum analogs for proof of work that could be more efficient than the existing paradigm.
But let's say you're trying to make something quantum safe, and as Gavin said before, sometimes people think something's quantum safe, and then some physicist somewhere in the world writes a paper, and it's like, oh no, it's not actually safe. Do you think future security systems, even on blockchain, will be able to automatically update when there's new methods of encryption?
Yeah, potentially. I think that but that's the risk, and always has been with cryptography, is you're in this race never ends, right? So there's always advancements in computing, advancements in algorithms. So it's a constant battle between the cryptographers and the cryptanalysts to basically do that. So it's always ongoing. I think the real concern for blockchain is that there needs to be rapid progress here, because it's not clear what's the best solution for post-quantum. We've proposed various solutions, but implementing that across these blockchains is a huge task. And it's very much not clear that the community is going to have to move very rapidly to make sure that everything's secure before quantum computing technology is there.
So let's say I'm a bank listening to this, because really banks have the same problem as Bitcoin has, which is that they could be hacked, and banks use similar kind of cryptography to keep all their systems secure. Almost everything on the internet uses some form of RSA or public key cryptography. And what should they do right now? Let's say they call you up and say, you got to help us. We want to make sure we're quantum safe.
Yeah. So I think a lot of the finance industry, and large industries, have been aware of this threat going back years, and they've been paying attention to it. So they do have a head start over other industries. Essentially they're going to have to be compliant and replace all of their RSA-based infrastructure with post-quantum schemes, whether that's in software or hardware. So they're going to have to work with vendors, make sure that they're compliant, or else there's a risk factor for their business.
How aware are they that they need to do that? I understand that Biden said you got to be compliant, but if I'm the head of IT at JP Morgan, and is my job depending on whether tomorrow I change the whole bank to be quantum safe?
Yeah, I think like all the banks have been very like forward thinking on quantum. I mean, there's a reason why Goldman Sachs and JP Morgan both have quantum research divisions within their company. And they've been looking at this for years, both on the security side and then also looking at speed ups for like options pricing and other things in terms of financial instruments. So yeah, I think they're all very aware of the threat, but now it's just a matter of finding the best solutions to implement, and that's where BTQ comes in. We've been developing these solutions and this specialized intellectual property that would be needed for certain use cases.
And Nick, as we were talking before the podcast started, I sort of feel there's two types of quantum computers. There's the companies building the quantum computers and maybe allowing access to them through the cloud. And there's companies like yours, which are building solutions that will be needed for a post-quantum world, meaning those solutions are actually needed right now in anticipation of the future at some point being post-quantum.
Right. Absolutely. Yeah. So yeah, as you mentioned, it like the security piece is very near term. It's already here. And you're seeing this adopted globally, and it's now very top of mind just given the recent Google announcement. But there's also been other major announcements. A company, I think out of Boston, QEra, announced an announcement last year. So you've seen a constant string of quantum computers, getting far better than just a couple of years ago. And of course, you have a lot of countries, whether that's in Asia or in Europe, that are developing and investing billions of dollars into this technology. So safeguarding data is going to be critical.
Now, is there any kind of Moore's law of quantum computing where, okay, quantum computers are going to have more qubits every 18 months, or is there anything that sort of makes sense out there?
Yeah, I mean, Gavin, we've developed some internal metrics for this, if you want to touch on that.
Yeah, so there does seem to be something like that. If you just chart the growth in numbers of qubits over time, we don't have a lot of data points because quantum computer companies have only been around since really 2010s, but it is showing kind of an exponential growth. Another important metric is the quality of the gates. We call that the fidelity, because you have to have really high quality gates to make things work. And that's also the error rates is going down in an exponential manner. So there is that kind of scaling, and you can make forecasts of when we would expect quantum computers could be big enough to, say, crack elliptic curve digital signatures. For example, that's used in signing for Bitcoin transactions. And when you place a proposed transaction in a block and you want to add a block to the blockchain in Bitcoin, you do require that digital signature. And there's a window before the transaction has been approved on the network of an average 10 minutes, where if a quantum computer could solve Shor's algorithm for the discrete log problem, they would be able to find out the secret key of one of of basically the owner of the signature, and then could start forging signatures. So if your quantum computer could be big enough to solve that problem in that time window of 10 minutes, that threatens the entire integrity of the network. So you can make forecasts on when that event will occur. And so that's something we look at BTQ.
When will it occur? What have you guys?
Well, so, like I said, there's a lot of still engineering problems, like how you connect these modules. but you can get sort of optimistic and pessimistic estimates. And the optimistic in the sense of go quantum is, early 2030s, maybe, 2034, 2035. Pessimistic would be more into like late 2030s, 2040s.
But to your point now, which is that if quantum computing gets to that point, then if someone takes a snapshot right now of every Bitcoin transaction, even though it's totally encrypted and we can't hack into that, they will be able to look back at the past. In the 2030s, they'll be able to look at the 2020s and figure out every transaction that occurred. And that itself could lead to a lot of, havoc and the world, collapsing.
Yeah, well, so there is this idea where you harvest now and crack later. Not so much with Bitcoin because people can use different public keys, so the future transactions won't be affected by past events. But certainly with like the U.S. government in protecting secrets, or any government, they're using oftentimes public key cryptography. And once that's out there, if you collect that data now, you could crack it later. So that's one of the real big incentives to move now to post-quantum cryptography, because exactly, you can just wait until the quantum computer is ready, and you learn those secrets.
And what if the model of quantum computing, what if people start thinking about it differently? Like right now, you're saying they're trying to reduce the error rate as you add qubits. What if I don't care about the error rate and I just add tens of thousands of qubits, knowing there's going to be lots of errors, and I just run repeatedly and have some way of confirming solutions, so the error rate could be huge, but I don't care.
Yeah, so that will not scale well. It'll turn out that just the number of ways for errors to occur will just accumulate to a point where it's just not going to work. And that's something we call the threshold theorem. There's an actual value of the error rate which you have to get below in order to have any hope of making things work as your size grows. And what's really cool is actually we're below that threshold in a lot of the quantum computer architectures now. That was one of the really big things about the Google announcement with the Willow chip, is they got below that threshold. And many other companies are doing that. So it's really exciting. It's something we've been looking to do for decades now, and it's happened. And that's why there's a lot of excitement in the air.
And for you guys, since you are a company and not just being theoreticians about it, do the Googles or IBMs, which have the money and resources to throw at this, do they scare you in terms of as competition?
So I think, a lot of the companies that are developing QCs, it's certainly an exciting space. So like at BTQ, we're not currently developing quantum hardware. We're focused on the quantum security side of things. And we've been building this intellectual property moat for a decade now, and are a first mover public company in the space, and have made 2 acquisitions in the past 6 months. And I think, we're kind of a differentiated in terms of our talent and IP and market opportunity that we're seeing. But you're certainly seeing interest from all those companies, and some of which we've been working with, and see them as strategic partners.
And let me ask you, I try to understand and look. I looked at kind of the quantum mechanics and math behind how qubits work and quantum computation happens. And it's really not understandable to someone who doesn't have a PhD in quantum mechanics, it seems to me. But do you think someone could develop a skill set as a quantum programmer or a programmer of quantum algorithms without necessarily understanding all the underlying quantum mechanics underneath?
It is a talent war out there, but I think on the software side, certainly you could get away with not. I'm kind of doing a PhD in the field, for sure. But I think you're going to see a lot of attention on just like talent in this space, just given how hard it is to find good talent. And but yeah, I mean, you can do like software engineering similar to computer science. I mean, you have the PhDs that are devising the very complex technology and algorithms, and then you have the software engineers that are higher level.
Right, you could be the best you could be the best programmer in the world of classical computing without understanding the nuts and bolts of how a computer works, how a semiconductor works, how a transistor works. I'm wondering if the same thing could occur for quantum programming.
Yeah, absolutely. We use these abstract models to represent things, and the reason like it took so long for people to come up with quantum computing is because it looked too simple. Like every single qubit you wouldn't think of as just a 0 or 1 back, like in the 20 or 1930s or 40s. You would have to think about where exactly this atom is sitting and all the electrons and protons, and it would be a very complicated object. It would take tons of blackboards to describe what that atom is doing. But because of all the experimental progress we've had, we're able to simplify it and abstract it as just the electron is in one state or another, and that's a 0 or a 1. And the same thing when kids will learn about quantum computers, they're not going to have to dig into all the physical details. They'll be able to think about it more as a game. And I think it's really exciting, like especially with AI, which can be a tremendous teaching tool, where you can use sort of natural language queries. You don't have to be hyper pedantic in how you ask a question, and get a reasonable answer. So yeah, I'm actually really optimistic that we're gonna start to change the ways we think to be more quantum. It'll be just part of school education.
You guys should write, just for like even like marketing purposes, guys should write a book, Quantum Computing 101, just to explain what it is, how people are going to start using it, how people could program in it, what sort of problems can be solved now, your version of the quantum Moore's law, like all these things. Like you should make a name for yourselves doing the Quantum Computing 101 book.
We have a lot of plans on the marketing and communication side, so we'll definitely keep you in the loop on that, James.
That's great. And here now, I'm going to ask the dumbest question of all, just to close this out. So, given that one can't understand kind of the, let's say, location of a particle until it's observed, how did the Big Bang happen?
Oh, just an easy question here.
Please tell me.
Yeah, I mean, these are the Big Bang is a way that is a consistent description of the physics we know, and it is a way to describe how the universe is expanding, why we get a certain ratio of matter to antimatter, and all these big questions. But why it happened, well, there are probably some people that have better ideas than I do, but I think these are still big mysteries.
All right. Well, at that, you have answered a lot of my questions. I feel like my understanding is a lot greater. I also want to add to anybody listening to this, if you want to tweet out questions that maybe we could answer later. What are your guys, or what's the Twitter account of BTQ?
I think it's just BTQ _tech. So yeah, btq.com is the website. So.
And what's your stock symbol?
Yeah, just BTQ or BTQQF in the US.
Yeah, because you trade in Canada, right?
Yeah.
Well, Nick, Gavin, thank you so much for your time. I really appreciate it. I feel like I finally am getting a grasp of what this is, what the timeline is, and why there is a particular urgency now for companies like yours that are doing solutions as opposed to building the actual computers themselves. So I appreciate you spending the time to come on here. And should I be pessimistic or optimistic about the universe, given that quantum computing will eventually happen? I feel like we're already too late to save things.
Optimistic.
Optimistic, yeah.
All right. I'm there with you. Good luck, guys. Thank you for your service.